Hello everyone, and welcome to this video titled Derivatives and the Shape of a Graph. This is part 3 on the second derivative test. So in this video, I'm going to be taking you through a preview version of a Knewton Alta Homework Assignment that is also called Derivatives and the Shape of a Graph, but I'm specifically going to be going over the objectives under the heading the second derivative test. So please understand that this is a preview of the assignment. So the questions that I work on in this video may not be exactly the same questions that you'll see when working on the assignment as a student. But the objectives should be the same, and the methods used to solve certain problems should also be very similar to what you're doing. Okay, so here we are at the Knewton Alta site. Again, this is a preview of, in this particular course, it's section 4.5, but this, derivatives and the shape of a graph homework. In the upper right-hand corner, right, you should be seeing a mastery bar that shows you how far along you've gotten in the assignment. Next to that, an activity log, which shows you all of the objectives in the assignment, right? There were 9 objectives here broken up into 3 headings. So I've already done a part 1 video on the first derivative test objectives and a part 2 video on the concavity and points of inflection objectives. All right, so this will be the last video, part 3 on the second derivative test on these 3 objectives here. So then back on the main screen, you have your current objective, a question beneath that current objective, related to that objective. And then at the bottom of every question, you should be able to find a feedback option. So if you see any issues with the question itself or the answer explanations after the question, you see problems, typos, mistakes, you can send feedback directly to Knewton's support. Hopefully someone will get back to you shortly with a way to fix your issues. Now, of course, you will not have the instructor cheat option. It's for instructors only to fill in correct answers, and I'm going to avoid using that during this video because you won't have it either. But you should be able to find a more instruction option. So if you're working on an objective and you forget what the material is about or how to go about doing something or whatever, click on the more instruction option and you'll be taken to some reading to do or some videos to watch or both related to that objective, and hopefully looking through that material will help you get through the assignment problems. All right. So this first objective is use both the first and second derivatives of a function to determine the basic shape of a graph. So I've already discussed these, what the first derivative and second derivative tell us about the graph of a function in the part 1 and part 2 videos for this assignment. So remember the first derivative, that will tell you where a graph is increasing or decreasing, going up or going down as you move from left to right. And remember the second derivative tells you the concavity of a graph, right? Which way it's curving. Is it concave up or concave down? So first question here, we're given a polynomial function. You're said, told to consider the function f of x below and some polynomial function here. So over what open interval or intervals, right, there may be more than one, is the function increasing and concave down? And give your answer in interval notation. And if for some reason there is no interval where those happen at the same time, you enter that empty set symbol. Okay, so let's go with some paper here. So this function we're given is, x to the fourth divided by 4. So, 1/4 for the coefficient times x to the fourth minus 4 times x to the third plus 256 times x and plus 2. All right, so to talk about where the function is increasing, I need to have the first derivative. So f prime, it's a nice, polynomial again, so simple term by term, apply the power rule and constant multiple rule and all that. So first derivative would just be x cubed minus 12x squared and plus 256. Right. So there's, the first derivative. And we're going to try to figure out, where is f prime positive? Because remember where that's happening, that means that's where f is going to be increasing. And where the derivative is negative is where the original function is decreasing. So this is a cubic. And it's not something that's, easily factorable, right? It does have integer coefficients, so I can apply the rational zeros theorem to determine some zeros and maybe help me factor this thing. Because remember, I'm trying to find critical points. Right, first, where is the derivative equal to 0? So where is f prime, equal to 0? Where is it undefined? But this is a polynomial, so it's, never going to be undefined. Now I'm gonna do a little shortcut here. I'm going to put this function into Desmos, right? So, sorry, I'm going to have the news up. So here's, again, the desmos.com site I've used many times in previous videos. Yeah, I'm just going to put that derivative function in. So x cubed, just to save some time here, minus 12x squared, plus 256. And you see how it's got, 8 is an x-intercept that would have an even multiplicity. See how it's bouncing off the x-axis there, and negative 4 is also a place where it's 0. And the derivative is positive between negative 4 and 8, right? So we're seeing that in this picture here. I'll zoom out a bit more. So again, the derivative is 0 at 8 and also at negative 4, and it's got a positive value, between negative 4 and 8, and also to the right of 8. Right, so I'm going to indicate that stuff here, right? This happens at x equals negative 4 and at x equals positive 8. And if you were to factor this, again, you would do synthetic division or something, right? Polynomial division, and say, hey, negative 4 is a 0, so x plus 4 would be a factor of this. And we saw that x equals 8 was a 0, so x minus 8 would be a factor. And then you saw how the graph was bouncing off the x-axis at this point, so it had an even multiplicity. That would tell me that it'd be x minus 8 squared. So if I were to factor this completely, it would factor this way. And we'll keep this in mind when we go make a number line here, right? So again, I'm going to make a number line. and this is representing possible values of x. I can plug into f here. The domain of f is all real numbers, so I'm looking at the entire x-axis. Now, above this, I'm going to put values of f prime, all right, above, and we're going to use the same number line for when I talk about concavity and the second derivative, just to save on writing, use the same number line. So, at, -4, the value of f prime is 0. Also at 8, the value of f prime is 0. And then if you were to plug in values around these, or, look back at that graph we just looked at, the derivative has negative values to the left of -4, positive values between -4 and 8, and also positive values to the right of 8. So remember what that tells us about f. So this interval from -infinity to -4, the graph of f will be decreasing. I'll just put a little down arrow here. And then the rest of the time, the derivative is positive. So f is increasing between -4 and 8, and then, continues to increase after 8, right, with the positive first derivatives. And we'll put a graph of f up later and see that that's happening. All right, so we got intervals of increase, intervals of decrease, but they also asked us, the question was this, right? The question was, where is the function increasing and concave down at the same time? So remember, to talk about concavity, we need the second derivative. So I do f double prime here, and looking at f prime, going term by term, doing the power rule. That'd be 3x squared, minus 24x to the first, which that's a nice easily factorable one right now, like the cubic was earlier. I can factor out a 3x from both these terms, and if I do that, you'd have x minus 8 left over. So my critical values for the second derivative, right, where the second derivative is 0, or where the second derivative is undefined. Again, this is a polynomial, so don't have to worry about it being undefined. This happens at x equals 0, and again at x equals 8. All right, so back on the number line, instead of making a whole separate one, I'm going to put values of the number line represents possible values of x, possible inputs. Above, I put the values of f prime, where that's positive or negative or 0. And then below it, I'm going to put the possible values of f double prime, right? So below this, I'm going to put my f double prime values. So at x equals 0, right, just make sure they're in the correct places. 0 would be somewhere in between -4 and 8. So at 0, f double prime is 0, right? So I'm indicating that like this. And then same thing at 8. The value of f double prime is 0 at x equals 8. And then knowing what we know about quadratics, this would be a parabola opening up if I graph this quadratic. So it'd be a, it would have positive values to the left of 0. And then it would have to have negative values. The second derivative would have negative values between 0 and 8. And then positive values again, to the right of 8. And each of these had a multiplicity of 1. Also, you could plug in values, to the left of 0, between 0 and 8, and to the right of 0 into my second derivative and see that it's positive and negative in these intervals, the way I've said. Now, we're looking for where is the function, right, the original function, this degree 4, where is it concave down? So remember that meant we're looking for where is the second derivative negative, right, less than 0. That's where f is concave down, right, curling downward. Concave down, right, something like this, it's a bowl that's dumping water. Well, if you look at our number line, the values of f double prime over the x-axis, from negative infinity up to 0, the graph of f will be concave up. So I'll put a little curl up like that. Between 0 and 8, f will be concave down, a little upside down bowl, curling down. All right, again, negative second derivatives. And then from 8 onward, from 8 to infinity, you got positive second derivatives. That's concave up. So we're looking for, where both of these things happen, where the function is increasing and where the function is concave down. So where the first derivative is positive and at the same time the second derivative is negative. So that's happening in here, right, from 0 to 8. See, from 0 to 8, first derivative is positive, so the function will be increasing, and the second derivative is negative, so it'll be, concave down. And that is the only interval where f prime is positive, and at the same time, f double prime is negative. So, my conclusion, f, the graph of f, and we'll take a look at the graph of f. F is both, increasing and concave down on the interval, from 0 to 8. And we're talking about open interval. Sorry, I put it sideways. I put infinity. 8. All right, that's 0 to 8. There's what I'm going to be entering, the interval from 0 to 8. Now, let's go to Desmos. I'll put this function in, and we'll see that. All right. So again, let's put in the original function, just f, right? F of x was this, 1/4 x to the 4th minus 4x cubed plus 256x, and then plus 2. And we said, between x equals 0 and x equals 8. So let me put in those points. Now 0, 2 would be the point at x equals 0. Right? There's the point 0, 2. And then I'll put in 8, the point 8, comma, f of 8. All right, so have it label it for me. So that's, the value of this function at 8 is 1026. So this is pretty steep, very steep. Probably not going to see it. It's going to look so thin. It's way up here. So it's very hard to tell then that, now, I mean, you can tell that it's increasing, obviously, right? I'm going from 0 to up to 8, 1026. So it's definitely increasing. But the fact that it's concave down is very hard to tell from this picture, right? Because it's so steep and so slight curve that you can't really tell. But what should be happening is something like this. You got the point, 0, 2, and you got the point, 8, 1026. So we're on a piece of curve that's, increasing and concave down, going up, but also part of this bowl that's dumping water, right? Curling downward. So again, hard to tell in Desmos, but it should be doing something like this. And I mean, it is. It's just hard to tell. But still, after all that, our answer here is the interval, from 0 to 8. And they said open interval, right? So parentheses on the ends. That interval is where, the first derivative is positive, so the function's increasing, and the second derivative is negative at the same time, so it's also, concave down. All right, then when you submit, it'll tell you if you're right or wrong, give you some encouraging words, but also give you an answer explanation. Whether you're right or wrong, I would highly recommend reading through these answer explanations. If you're correct, maybe you did the problem in a very inefficient way, and when you read through the answer explanations, you see that they're doing something in a faster way, a more efficient way than you are, and you might want to try that for future questions that are similar. Definitely read through if you got it, if you got it wrong. Try to figure out, where you went wrong, and hopefully you can learn from your mistakes for future questions that are similar. Okay, so now we get into the title of the heading on these three objectives is the second derivative test. So back in part one, we talked about the first derivative test to locate those, tops of hills and bottoms of valleys on graphs of functions, right, where those local extrema were. So this is another test to do the same thing. All right, it's the second derivative test to find local extrema. So let me discuss that real quickly first before we do this question. So this is the second derivative test. Just like the first derivative test, this is to locate, to find or identify, local extrema, right, where those tops of hills and bottoms of valleys are, where the turning points are, right, where the function's going from increasing to decreasing and decreasing, increasing. So here it is, our second derivative test. So given function, right, something that's twice differentiable, meaning it has a first and second derivative. That's kind of implied here. So to say, given a function, a differentiable function, f, first we're going to find the critical values of f prime, the critical points of the first derivative. So again, this is find out where f prime is equal to 0 or undefined, right, or where it's undefined. Remember that, because remember these are the locations where you could possibly have these local extrema, right? The only places where you could possibly have these hills and valleys are where the derivative was 0 or where the first derivative was, undefined. Now, the one that's going to probably be showing up most often is where the derivative is 0, and so I'll put some stars around that. That's the one we're going to probably work with most. But still, remember, wherever it's undefined, as long as that value is in the domain of the original function, you could possibly have a local extreme there. All right, so then we take these values and we're going to plug them into the second derivative, right? This is the second derivative test. So plug the critical values of the first derivative, right, the ones you find here, plug the critical values of f prime, plug those into f double prime, right, the second derivative. Now here's the test. If the value of the second derivative is negative, so less than 0 at this critical value, well, that means f will have a local extreme, has a local maximum at that critical value, right? Because if you're at, again, say you're at some point, so you're at a piece of curve like this where there's a top of a hill like this. See how the first derivative would be 0. So again, f prime would be 0 at this point, but it's curling downward, right? You see how you're on a piece of curve that's curling downward when you're at the top of a hill like this. So the value of the second derivative would be negative. So if you find where the first derivative 0, plug it into the second derivative. If that's negative, that means you have a local maximum. Now, if the second derivative is positive, Well, then that means you're on part of a curve that's curling upward, concave up. So in those places, f will have a local minimum value. You'll be at the bottom of a valley, bottom of a dip, right? You'd be on a piece of curve like this, right? Where that point at the bottom, if it's nice and rounded like this, right? The value of the first derivative is 0, right? You have a critical point there. But you're on a piece of curve that's, holding water. It's curling up. So the value of the second derivative is positive. Okay, so you find these critical points, find the place where the derivative is 0, plug it into the second derivative, and if it's positive, a positive value, that means you've got to be at the bottom of a valley. You've got to be at a point where the function has a local minimum value. Now, what if it's, still 0 or undefined? So if the value of the second derivative equals 0 or, say, undefined, then the test is inconclusive. They say the test can't tell you anything. The test is inconclusive. That means you should just go back and do the first derivative test to see if you're at the top of a hill, bottom of a valley, right? If you're going from increasing to decreasing or decreasing to increasing. So you can remember you can use the first derivative to tell you that stuff. So if you can find the critical values from f prime, plug them into f double prime. If it's 0 or just not defined there, this second derivative test doesn't tell you anything. So, use the first derivative test, right? Go back to what we did in part 1 of the videos for this particular assignment. All right, so now I've got this discussed. Let's go and work a problem where we're asked to, use the second derivative test to find local extrema, right? So local maximum values, local minimum values of a transcendental function. So those are your non-algebraic functions, right? Your trigs, inverse trigs, exponentials, log, hyperbolic, something where it's not adding, subtracting, multiplying, dividing variables, raising variables to powers, or, taking roots. Right? All that stuff was algebraic. This is non-algebraic stuff. Anyway, so here, use the second derivative test to find the location of all local extrema in the interval from 0 to 2 pi, right? Just between 0 and 2 pi, though, not including 0 or 2 pi, right? For those are parentheses. So look, we're asked to find the location. So that's the x values, right? So we're only asked for the locations. Where do they occur? So what are the x values? Where these hills and valleys will occur? So you see they only want the x values down here, right? The local maximum values, maxima will occur at certain x values. The local minima, right? Minimum values will occur at certain x values. So just, you don't have to plug them in and see how high or low the hills and valleys are. You just have to indicate where they occur. Now we'll look at a graph as well and see how high and low they are. But, where do they happen? Okay. So we're given this function, f of x equals, and this is a trigonometric function. It's got cosine here. You got -4 times the cosine of 3x, then -4, but we're only going to look on the interval between 0 and 2 pi. So just find critical values in here. So like I was saying, take the first derivative. So this would involve chain rule, right? So I take remember the derivative of cosine of something is, negative sine of that thing. So we'd have negative sine times -4 of 3x, and then multiply by the derivative of 3x, which would be 3. So this would be +12 times the sine of 3x, and then plus nothing for the constant, right? But there's your derivative function. And then we're looking for critical values of the first derivative, right? So where is the derivative equal to 0? Just in this interval, though. So remember how to solve trig equations with arguments that are not just a single variable, not just theta, not just x here. We have 12 times the sine of 3x. When is that equal to 0? No, it's never going to be undefined, so I'm not worried about that. So that's when the sine of 3x equals 0. And remember the input here, this 3x. Remember the values of sine that have outputs of 0. 3x can be any multiple of pi. So I'll put k times pi, where k, for k an integer. All right, I could put 0, 1 pi, 2 pi, negative 1 pi, negative 2 pi, whatever. So that means the value of x, just x itself, would be some multiple of pi over 3. And then we're just going to take the multiples of pi over 3 that are between 0 and 2 pi here. So again, when k is 0, you get 0. I'm not using that. And then you got, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, and then 6 pi over 3 is 2 pi. So that's not included in the interval they gave us. So here we go. These 5 values. So these are where the derivative is 0. These are where I could possibly have the top of a hill local maximum or bottom of a valley local minimum. So this second derivative test is, all right, let's take the second derivative. So again, f double prime would be 36 times the cosine of 3x. So I'm using chain rule there. I'd have to multiply by 3 again, right? The derivative of the sine of something is the cosine of that thing, and then times the derivative of the thing inside. And 12 times 3 is 36. So it's 36 times the cosine of 3x. 3x, sorry, not pi. That's an x. So 36 cosine 3x. And then I'm just going to plug these values in, right, to this f double prime function and see what we get. Right, so I'm going to make a little table out of them and see if we get positive or negative values. Now, every single one of these, when I plug this in, I'm getting some multiple of pi. When I plug in pi over 3, 3 pi over 3 is pi. Remember the cosine of pi is -1, so I get a value of -36. And because this is a negative value, means it's concave down there, right? So that means I have a local max. F has a local max at x equals pi over 3. You'd be at the top of a hill, someplace where you're concave down. And then when I plug in 2 pi over 3, it's the cosine of 2 pi, the 3 cancels. Cosine of 2 pi is 1, so I get positive 36. And if the value of the second derivative is positive, that means I'm on a piece of curve that's concave up. I'm at the bottom of a valley, so f will have a local minimum at, x equals 2 pi over 3. And then hopefully you see how it's going to alternate here, right? When I plug in pi, the cosine of an odd multiple of pi, 3 pi would be -1. So I get -36 again. So again, I'd be at the top of a hill, someplace where there's a negative concave down, right? So the graph of f will have a local max again, and if I plug in 4 pi over 3, that'll be the cosine of 4 pi, which is the same as the cosine of 2 pi, or 0, which is 1, times 36 is 36 again. That's a positive value, so I'm on a piece of curve with a concave up. F has a local minimum value there at x equals pi over 3, 4 pi over 3. And then 5 pi over 3, once again, I plug that in. I'd have the cosine of 5 pi, which would be -1, times 36 would be -36. So again, the second derivative is negative at this value. I'm on a piece of curve that's concave down, so we're at the top of a hill, right? We have a local max. So there are, 1, 2, 3 values where I'm at the top of a hill. All these odd multiples of pi over 3, 1 pi over 3, 3 pi over 3, 5 pi over 3. And then a local mins, there's 2 points where you have the bottom of a valley where you have a local minimum value, and that's at the even multiples of pi over 3, right? 2 pi over 3 and 4 pi over 3. Now let's go take a look. I mean, I might as well take a look too since I got Desmos pulled up. Make sure you're in radian mode. Don't forget that when we're working with trig functions in calc class here. So the function we were given initially, right, f was this -4 times the cosine of 3x and then -4. And I only want to look at it from 0 to 2 pi, right? So 0 less than x less than 2 pi. Close the braces. So there. Change the color on this. All right, just so it doesn't blend with the axes. So there's the piece of graph we're looking at. And you see how, again, when you click on it, the nice thing about Desmos is, you click on it, it'll show you where these turning points are, right? Where the tops of hills and bottoms of valleys are. So you see there's 3 of them, right? At pi over 3, pi, and 5 pi over 3. And then there's 2, bottoms of valleys here at 2 pi over 3 and 4 pi over 3, just like we said in our chart on the paper I was drawing. So local maximum values occur at, let me bring up the basic keyboard that'll have pi in it, right? So one was at pi over 3, pi over 3, then separated by commas, they said, so because there's multiples of these, right? Pi over 3, pi, and then also, 5 pi over 3. So at those values, you had the top of a hill, you had a local maximum value, and then there were only 2 x values, 2 inputs, where you were at the bottom of a valley or at a local minimum, and that was at 2 pi over 3, comma, and 4 pi over 3. And this should be good, right? We're only asked for the locations, not the actual outputs themselves, not the y coordinates. Great. And they probably have a picture. They should have a picture. They don't have a picture of it, right? So this is what we're looking at. That function over the interval from 0 to 2 pi, where the hills and valleys are. All right. All right, so back to that objective where you're talking about the shape of a graph, right? Where a function's increasing or decreasing, concave up, concave down. So it's another polynomial function here, right? This degree 3 polynomial. And we're asked over what intervals is the function, both decreasing, so it has a negative first derivative, and concave down. So that means has a negative second derivative. So negative first derivative and negative second derivative, decreasing, concave down. All right, so let's write this out. So the function I'm given is 1/3 times x cubed, right? It was x cubed over 3, plus, 15 halves times x squared, right? It was 15x squared over 2, plus 50x minus 2. So to talk about where this is going to be increasing or decreasing, I need the first derivative, talk about the critical values and stuff, where it's positive or negative, right? The first derivative. So that's going to be x squared plus 15x and then plus 50. If I just use the power rule and all that, every term there. Now this is a quadratic, so if I want to see where this is 0, I could use the quadratic formula or complete the square method, but this is another nice factorable one. This should factor to x plus 10 times x plus 5. Right? That would multiply to be x squared plus 15x plus 50. So my critical values are, x equals -10 and x equals -5, right, where the output would be 0 for this first derivative. And then like in that first problem like this, for this objective, Here's a number line representing possible values of x. On the top above the line, I'm going to put values of f prime. So we got, at negative 10, the value is 0. At negative 5, the value of the first derivative, f prime, is 0. And then once again, knowing what you should know about quadratics, if I were to look at the graph of this derivative function, it would be a parabola opening up, have positive values to the left of negative 10, then negative values, again, you can plug in values around here and see, between negative 10 and negative 5, and then positive values, to the right of negative 5, okay? So the function f, all right, so the original cubic polynomial function will be increasing on the interval from negative infinity to negative 10. It'll be decreasing, which is what we're asked for, right? Where is it decreasing and, concave down? So we'll figure that out in a second. But it should be decreasing between negative 10 and negative 5, and then increasing once more to the right of negative 5, from negative 5 to infinity. All right, so I know where the function is going to be increasing and decreasing, but now I also want to discuss where it's, concave up and concave down. So that's where the second derivative is going to come into play. So I take the second derivative, which would just be 2x plus 15. All right, so there's only one, this is a linear, you set that equal to 0, it's never undefined. The only critical value here would be negative 15 halves. All right, if I were to set this to be 0, I'd subtract 15 divided by 2. Now that's negative 7.5, right? So that's actually exactly halfway between these two. All right, that is actually the average of negative 10 and negative 5, right? Negative 15 halves. So again, on the bottom part here, I'm going to put the values of the second derivative. So again, be careful with the labeling, right? So down here, I'm putting the values of f double prime. At negative 15 halves, the value of the second derivative is 0. And then knowing what you know about linear functions, right? This is a positive slope, so it would be a line going up, up to the right. So there should be negative second derivatives to the left of negative 15 halves. And again, you can go ahead and plug in values to the left of negative 7.5 here. For the second derivative, you'll get a negative value back. And then to the right of negative 15 halves, you got positive second derivatives, right? Plug in numbers to the right of negative 7.5, bigger than negative 7.5. And this second derivative should have a positive value. Now remember what this says about f, right? About the original. So to the left of negative 15 halves, the graph of f will be concave down, right? Curling downwards, got a negative second derivative. But to the right of negative 15 halves, the graph of the original, the graph of f will be concave up, right? You got a positive second derivative. So there'll be an inflection point at negative 15 halves. Remember when you change concavity like this, but we're not asked for that, right? We're just asked for on what interval is the function f, right? The original we were given. Every conclusion we make is about the original. On what interval is the function both decreasing and concave down? And that would be between here and here, right? Between negative 10 and negative 15 halves, right? In this interval here, got a negative first derivative, so the function's decreasing, and also a negative second derivative, so the function's concave down. So I'm going to put the interval from, and that's the only one, right? That looking at this number line here, that is the only interval where both the first derivative and the second derivative are both, negative. So I'm going to put, from negative 10 to negative 15 halves in my interval notation, right, with the parentheses and all that. So in the interval from negative 10, comma, to negative 15 halves, close the parentheses there, that is the only one where this graph will be both decreasing and concave down. And you can go to Desmos and verify that if you wish. But if it's really steep, like that first example, you might not be able to tell immediately just by looking at it. All right, great. All right, so now we're the other objective we haven't touched yet, but it's still the same as that one with the transcendental functions with the cosine that we saw earlier. It's, again, it's use the second derivative test to find these, hills and valleys, tops of hills, bottoms of valleys, these turning points where a function goes from increasing to decreasing or decreasing to increasing, right? These local extreme values. So given this function here, now it's asking about a particular interval again, right? So the just like that first problem, right, we were just on the interval from 0 to 2 pi. Here we're using the second derivative test to find the location of all local extrema. Right? So where do they occur, at what x values do they occur? Just in between 0 and 6. Okay, so just between 0 and 6. So if you find values outside this, you're not going to worry about them, right? Don't enter them for this function here, this rational function. Again, if there's more than one, put commas between them. And if it doesn't have any, right? If it doesn't have a local max or a local min, you're going to enter that empty set symbol. And answer should be exact, meaning, don't punch them into a calculator and round, right? Leave them the way they are, the way you find them. All right, so I'm given this, this rational function here. So in the numerator, we have 4 times the quantity x minus 10, squared. And then the denominator is simply x minus 6. All right. So again, we're only looking on the interval between 0 and 6, right? 0 to 6 with parentheses. Right? So just looking for critical points, hills and valleys between 0 and 6. All right, so first I need the critical points of f prime, right? That's where these hills and valleys could occur. Now I'm going to use the quotient rule here. All right, it's a fraction. So remember quotient rule, and we'll of course simplify this when we're done because I also want to find the second derivative, right? They're asking us to use the second derivative test. So remember this is denominator, so x minus 6 multiplied by, now the derivative of the numerator would be 8 times x minus 10 to the first, and then times the derivative of x minus 10, but that's just 1. So it'd just be 8, I'll throw the 8 out front here, times x minus 10 to the first. All right, so denominator times the derivative of the numerator, and then minus, then the numerator, 4 times this x minus 10 squared, times the derivative of the denominator is just 1, so I'm not going to put that. You can put times 1 if you want. And then all of that, right, everything I just wrote, divided by the denominator, this x minus 6 squared. Okay. Now, I'm going to simplify the top up here. So notice how both of these products, and the one before the minus and after the minus, they have a common factor of 4, right? 8 is 4 times 2, that's 4 times 1. They also have this common factor of x minus 10, right? There's one x minus 10 here, and there's 2 of them here. So I'm going to factor that out, 4 times x minus 10. Now when I remove that, you'd have 2 times x minus 6 left over in that first product. And then minus, right, still the minus there, and then, just one of the x minus 10s left over here. All right, all that together. And we'll distribute this negative, distribute this 2, and combine stuff. And again, all this is divided by x minus 6 squared. Now, if you actually combine like terms in this factor here, you'd have 2x minus x, which is 1x, then minus 12 plus 10. So we got 4 times x minus 10. And then again, this factor here is 2x minus x, so x, and then negative 12 plus 10, so minus 2. And then all over, x minus 6 squared. Okay. this is going to be undefined at 6. So again, the critical values that are in the interval that they gave me. All right, so again, 6 makes this undefined, but that's not even part of the domain anyway. That's not even part of this interval anyway. So I'm not going to mark it down. But what makes this 0 are 10. All right, if x were 10, the numerator would be 0. So the whole thing would be 0. But again, 10 isn't in this interval. So I'm not going to worry about that either. So all that really is going to be that I'm going to focus on is the number 2, right? When x equals 2, right, this is factored up here, the numerator would be 0. So the only critical value of f prime that's in the interval in question is x equals 2. All right, so then to perform the second derivative test, I need to then plug this into the second derivative, right? So I need to take the derivative of the derivative. So again, I'll leave it this way. I'm going to use the maybe I'll multiply the top part out just to make it easy on myself, right? So this would be, if you multiply these two, that'd be x squared, minus 10x minus 2x. So x, this is 4 times x squared minus 12x, then plus 20. And then that, again, the numerator is distributing the 4 would be 4x squared minus 48x plus 40, or sorry, yeah, plus 80, 80, 80, right? Distributing the 4. All right, so then the second derivative, and I'm going to use the quotient rule. So it's, denominator, so this x minus 6 squared times, and then the derivative of the numerator, which is kind of why I wrote it this way. So I can just do the power rule term by term instead of doing the product rule with this. Because if I left it this way, I'd have to do the product rule. But if I do the derivative of the numerator in this form, it'd be 8x minus 48. So there's your denominator times the derivative of the numerator, then minus, and then the numerator. Which if you want to write it in factored form, again, you could. Times the derivative of the denominator would be, 2, I'll throw the 2 out front here, times x minus 6 to the first. And then all that divided by the denominator squared, so that'd be x minus 6 to the fourth. Now what I'm going to do is, to use this second derivative test, plug 2, right, the only critical value from f prime we found that was in this interval, plug 2 into this and see if it's positive or negative. So the second derivative at 2, now the nice thing is, right, if you thought about this in factored form, remember this here, this 4x squared minus 4x plus 80, that's the same as 4 times x minus 10 times x minus 2. So when I plug 2 in to this, right, one of the factors of this is going to be 0. So I'll have minus 0 from that. And then this part is, negative 4 squared, right, 2 minus 6 times, and then, 8 times 2 is 16. I could have factored the 8 out, made that x minus 6 cubed, whatever, but like 8 times 2 is 16, minus 48 is negative 32. And so the numerator is negative overall, because this is positive times a negative, so this is a negative numerator. And the denominator is once again, 2 minus 6, to the fourth. Take a negative number to an even power, that's positive. So overall, this is a negative value, right? It is less than 0. Again, I don't really care exactly what it is. All I care about is it positive or negative? So putting this together, all right, critical value at 2, and the value of the second derivative at 2 is negative. That means I'm on a piece of curve that's concave down. So we're at the top of a hill. That means f has a local maximum at x equals 2. And that's it. That's the only one. So no local minimum. I'm going to put that empty set symbol for where the local minimum occur. Now let's take a look at a graph here. I actually want to verify this. So here was the function we were given, right? F of x equals, you had 4 times the quantity x minus 10 squared in the numerator and x minus 6 in the denominator. But only between, let's see, okay, we're doing here. Only between 0 and 6. Right, so let me put those braces in, right? Braces 0 less than x less than 6. So we're just looking at this piece of the curve. You know, now 6, there's an asymptote, so it's going down forever, right? You can't, x can't be 6. And you see there's top of a hill, there's a local maximum when x equals 2, this 2 negative 64 point, and no bottoms of valleys, right? There's no local minimum. So that x equals 2 point was correct. Right? So local maximum occur at x equals 2, and there is no local minimum value. So again, you're entering that empty set symbol, which is here under the basic keyboard. Right? Oh, nope, it's in the sets keyboard. My apologies. So that circle with the slash through it symbol, because there's no local minimum in that interval. Okay. All right, so another second derivative test to find local extrema for algebraic functions. Now this one, look, they just give you, it's a select all that apply. Right? So we're asked to consider a continuous function f. The function has critical points. You know, these are for the first derivative, right? -7, -2, +7. The table below shows the critical points of the function and the sign of the second derivative at each critical point, at which value or values of x are local minima, minima guaranteed to occur. So remember, that's where, if you're at the bottom of a valley, right, you're at a place where there's a local minimum. Remember, that's where you're on a piece of curve that's concave up. So it would have a positive second derivative. So these critical points where the second derivative is positive, plus signs here, that's where the function f would have a local minimum. And then this point at x equals 7, where the second derivative is negative, that's where you'd have a local maximum. So the only ones we're selecting, again, are the ones where a local minima is guaranteed to occur. Minimum, that's at -7 and -2. So pretty simple one there with the chart and all the positives and negatives already identified. Great. All right, so another one with the shape of a graph, where is a function increasing or decreasing and concave up or concave down. All right, so like the first example, first question from this, I'm given some degree 4 polynomial, and I'm asked, what over what intervals is this function both increasing and concave up? So positive first derivative and positive second derivative. All right, so here's our function. Degree 4, we get 1/4 x to the 4th minus 2/3 x cubed minus 2x squared plus 8x and then minus 8. So again, talking about where it's increasing or decreasing, I need to know the first derivative. So that'd be 1x cubed minus 2x squared minus 4x and then plus 8. Okay, this one here is It's actually factorable by grouping. So if I pulled x squared out of the first two terms, you'd have x minus 2 left over. And then if I pulled a negative 4 out of the next two terms, you'd have, x minus 2 again left over. And then you can factor x minus 2 out of both of these, or you might recognize this. Oh, yeah, whatever. So x minus 2 out of both of those, and if I remove x minus 2 from both these products, you got x squared minus 4 left, and that's a difference of squares. So you have x minus 2 times, and then this factors to x minus 2. So that would give me another x minus 2. So I'd have x minus 2 squared times x plus 2. All right, so the critical values. So again, you could, if you recognize that you can factor it pretty easily, go ahead and do that. Or you could do what I did earlier, right? Kind of cheat a little bit. Go to Desmos, punch this cubic in, and see where the x-intercepts are, right? To be able to know how to factor it, see where the critical points are. So the critical values are x equals positive 2 and x equals negative 2. All right, that would make each of these factors 0. And again, you can plug them back into the original and see that you get a value of 0 both times. All right, so number line and values of x. Now again, on top of the number line, I'm putting values of f prime. Say I add negative 2, it's 0. At positive 2, it's 0. And then hopefully, again, I'm just going to kind of, you should know some stuff about polynomial functions. This is an odd degree positively coefficient. So it should be negative on the left end. So negative values up until negative 2. Now negative 2 has a multiplicity of 1, right? This is x plus 2 to the first. So it's going to switch signs on me. I'll go to positive values between negative 2 and positive 2. But then positive 2 has an even multiplicity, so it doesn't switch signs around that one. It's going to stay positive to the right of 2. So again, you can plug in values around this to verify this, but the value of f prime would be negative for x values less than negative 2. It'll be positive for values between negative 2 and 2, and positive again for values to the right of 2. So what does that tell me about the graph of f, right? So the graph of f is decreasing to the left of negative 2, and then pretty much just increasing the rest of the time. It's increasing up until x equals 2, and then, continues to increase after that. All right, so then where is it concave up, concave down? So now I go to the second derivative. So first derivative like this would be easy to go term by term, get the second derivative, right? You'd have 3x squared minus 4x, and then minus 4. And again, when you're trying to find the critical points, you could, this is a quadratic, you could set it equal to 0, right? Use the quadratic formula if you want. But 3 times negative 4 is negative 12, factors of negative 12 to add up to negative 4, negative 6, and positive 2. So this is factorable. All right, this would factor to one of them would have to have 3x, the other has x. Again, I need a negative 6 and a positive 2 to show up. So minus 2 here, plus 2 here. All right, that'll give me minus 6x plus 2x for the minus 4x, and then minus 4 when I multiply these out. So the critical points for the second derivative are x equals negative 2/3, right? That makes this factor 0, the 3x plus 2. And x equals, positive 2, where this factor 0. So again, back on the number line, I'm going to do this below. Put f double prime, or we're going to indicate the values of f double prime down here. Now, again, at x equals 2, the second derivative is also 0. And then at negative 2/3, now negative 2/3 is somewhere between, negative 2 and 2. It's not the average like that one before. It's closer to negative 2 than it would be, the average would be 0. So it's not exactly halfway between them. So at negative 2/3, again, the second derivative is 0. And then, once again, knowing what we should know about quadratics, right? If I were to look at the graph of this quadratic, it would be a parabola opening up on, going up on both ends. So it should have positive values on the left end, right? Positive values up until negative 2/3 here. Then it's 0, and then it should have negative values between negative 2/3 and 0 and 2. and then it's 0 at 2, and then positive values, to the right of 2. And once again, what that tells us about the original, what that tells us about f, is that up until negative 2/3, the graph of f is concave up, right? It's got positive second derivative. And then between negative 2/3 and 2, f is concave down. And then to the right of 2, f is back to being concave up, right? So they wanted, where is this function, right? This degree 4 function up here, where is this function both increasing and concave up? So positive first derivative, positive second derivative. So there are multiple places. So between negative 2 and negative 2/3 here, between negative 2 and negative 2/3, positive first derivative, increasing, positive second derivative, concave up. And then from 2 to infinity, right? From 2 onward, got a positive first derivative, positive second derivative, so increasing, concave up. So there are 2 intervals here, one from negative 2 to negative 2/3, and then the other from 2 to infinity, right? So, and I'll be using the union symbol here, right? They just said put it in interval notation. They didn't mention anything about a comma separating the intervals. So one interval where this happens is, negative 2 up to negative 2/3. And then the union symbol, which is in the sets keyboard. And then from positive 2 to infinity, infinity's back on the basic keyboard, right? And there, that should be good. They close the parentheses for me. These are the intervals where the functions, again, both increasing and concave up. And you can look at it in Desmos if you want to verify that further. All right. Great. All right, so another one where we're asked to use this second derivative test, but just on a specific interval. All right, so again, maybe I'll go to Desmos again, just look at it between negative 2 and 5. So we have this polynomial function just on the interval between negative 2 and 5, and where are the hills and valleys, right? Where are the local maximum values and local minimum values going to occur at what x values? So once again, got a polynomial function. So here's what we're given. So it's negative 5/3 times x cubed plus 10x squared, and then minus 15x, right? But we're only going to focus on the interval between, negative 2 and positive 5, right? Okay, so first, where the hills and valleys could be are at the critical points for the first derivative. So take the first derivative, and we're going to see where it's 0, where it's undefined. Again, being a polynomial, not going to be undefined, right? So where is it 0? So that'd be negative 5, x squared plus 20x, and then minus 15. And again, I could use the quadratic formula here to find where this is 0. But this looks like it might be factorable. If I pull out a negative 5 from this, you'd have x squared minus 4x plus 3, and that factors to x minus 3 times x minus 1, right? So that's an easy way to look at it when you want to find critical points. All right, so my critical values, again, the only ones I want are in the interval from negative 2 to 5. Are positive 3 and positive 1. Well, both of those are, right? X equals 1 and x equals 3, right? Both of these values are between negative 2 and 5. All right, so then what we're going to do is, again, they want us to use the second derivative test to state where these, high valley, the tops of hills and bottoms of valleys are. So I go to the second derivative, and that would just be, negative 10x plus 20. And we plug these in to the second derivative. See the values. Now the value of the second derivative at 1 would be positive, right? Negative 10 plus 20 is positive 10, greater than 0. So that means f has a local minimum at x equals 1. right? Because if you have a positive second derivative, that means you're on a piece of curve that's concave up, so you're at the bottom of a valley, right? A place where there's a local minimum. And then the value of the second derivative at the other one, right, x equals 3, would be negative 30 plus 20. That's negative 10, a negative value. So I'd be on a piece of curve that's concave down. That means f has a local maximum at this point, right? At x equals 3, you're on a piece of curve like this. You'd have to be at the top of a hill. So local max at x equals 3, local min at x equals 1. That's what I'm answering. And again, you can go, I'm not going to do it this time, it's just a polynomial, but you can go to Desmos and enter this and look at the function just between negative 2 and 5, and you'll see you'll be at the top of a hill at x equals 3 and bottom of a valley at x equals 1. So local max occurs at x equals 3, local minimum at x equals 1. Great. All right, so then another one where we're using the second derivative tests. This looks pretty similar to a function we saw earlier, right? Another problem like this with the algebraic functions. Once again, just on a specific interval, right? Just between, we're only looking for critical values, points where there's hills and valleys, local maxes and mins, between negative 21 and negative 9. So again, I'll write this function out. We'll look at the first derivative. Now it's another one where I'll be doing the quotient rule. So we got 7 times the quantity x minus 1 squared in the numerator and x plus 9 in the denominator. So obvious, and again, we're only going to be on the interval from negative 21 to negative 9, right? Because you can't plug in negative 9 anyway, right? That shouldn't be in here. Even if you look at the domain of the whole function, negative 9 is not included. All right, so first derivative. So I'll go through the quotient rule. So it's the denominator x plus 9. Derivative of the numerator would be 14 times x minus 1 to the first, then minus, and then the numerator times the derivative of the denominator, right? So 7 times x minus 1 squared, and then times 1. Divided by the denominator squared. Now up top in the numerator there, again, this factors, they both have, both these products have 7 times x minus 1 as a common factor. And then what would be left over would be 2 times x plus 9. And then minus x minus 1 minus the 1. You have another x minus 1 still left over here. And then this whole factor here, distribute the negative here, distribute the 2 here. And we got x plus 9 squared in the bottom still. So I'd have 7 times x minus 1, and then again 2x minus x for 1x, and then 18 plus 1, 18, 2 times 9, 18, and then minus negative 1, 18 plus 1 for plus 19. All right, divided by this, x plus 9 squared. Okay. So again, negative 9 makes it undefined, but we're not worried about negative 9. It's not in this interval. Positive 1 makes the numerator 0, right? Positive 1 would be a critical value as well. But again, positive 1 is not in the interval in question. So the only critical value I'm going to work with is negative 19, right? Negative 19 is the only critical value in this interval, between negative 21 and negative 9. So x equals negative 19. All right, so then we're going to plug this into the second derivative, right? They want us to use this second derivative test. And you can multiply this out like I did before. No, I'll just leave it this time. So the second derivative, f double prime. Again, I'd be going through the quotient rule once more, so it's, denominator, it's x plus 9 squared times, and then the derivative of the numerator, I'm going to do 7 times, and then the product rule, maybe brackets and parentheses here, so it's, first times the derivative of the second, so x minus 1 times 1, plus, and then, x plus 19 times 1, so there's the product rule. Again, the constant multiple of 7 would stay around. So this is actually 2x plus 18. All right. So we'd have 7 times 2x plus 18 for the derivative of the numerator. Then minus, the numerator, 7 times x minus 1 times x plus 19, times the derivative of the denominator would be 2 times x plus 9. Then all that divided by the denominator squared. So x plus 9 squared squared, now that would be x plus 9 to the fourth. Now this could actually simplify quite nicely. This 2x plus 18, this is 2 times x plus 9. So you really have x plus 9 cubed times 14 in this first term, and you also have 14 times x plus 9 in the second term. So I could factor out a 14 times x plus 9, and then what would be left over? You'd have x plus 9 squared left over in this first product. All right, if I pull out 14 and x plus 9, you have this x plus 9 squared still there. And if I then minus, and if I pull out 14x plus 9, you got this x minus 1 times x plus 19 over here. And all that divided by x plus 9, to the fourth. And then one of the x plus 9s will cancel. All right, so this becomes x plus 9 to the third down here. And then if you actually multiply this out, this is, x squared plus 18x plus 81. That's x plus 9 squared. And then, minus this, all the stuff when you multiply x minus 1 and x plus 19. So we minus x squared. And then you got, plus 18x, so minus 18x. All right, we're subtracting that. And then negative 19, so minus that would be plus 19. And look, the x squareds go when you subtract, the 18x's go when you subtract. So I just have 81 plus 19, that's 100. So the numerator is just 1400, right? This is 14 here, this is 100, this thing in the braces here, divided by x plus 9 cubed. So that's a very, very simplified version of the second derivative. And then when I plug my critical value into this, so the second derivative at, negative 19, you have a positive numerator and a negative denominator, right? This would be negative 19 plus 9, negative 10 cubed. That'd be, negative 1,000. Positive numerator, negative denominator would be a negative value, right? Less than 0. And I don't really care exactly what it is, just that it's negative. So f has a local max. Right, we're on a piece of curve that's concave down. We'd have to be at the top of a hill at x equals negative 19. And once again, you can go to Desmos, punch this in, look at the interval just between negative 21 and negative 9, and you'll see that the point at the top of a hill there has x equals negative 19 as, the x coordinate. So in this interval, local max at x equals negative 19, and there was no other critical value, right? There was no other critical value in that interval. So no local minimum. So put that little empty set symbol in that box there, and that should be good. All right, so that objective's done with the algebraic functions using the second derivative test. All right, so here's the shape of a graph one again. Again, very similar to other ones where I'm given some polynomial function and asked where it's increasing or decreasing and concave up, concave down. So this time I'm asked where over what intervals is this function, both decreasing and concave up? So that means negative first derivative, positive second derivative. So again, the polynomial here. So we have 1/4 x to the 4th minus 75 halves x squared, then minus 250x, and minus 4. So there's our original. Let's talk about where it's increasing or decreasing, right? We're looking at the first derivative. So that'd be just 1x cubed minus 75x, then minus 250. Now I could go back and make it, again, I could kind of cheat a little bit, look at the graph of this, see where it's equal to 0. But one thing I see right now is that 5 would be a 0, right? And I'm gonna do synthetic division over here to see how it factors. So again, you got 1x cubed, 0x squared, negative 75x, negative 250 for the constant term, and I'm plugging in 5. So remember how this works, you drop the lead coefficient, then multiply, add, right? 5 times 1 is 5, plus 0 is 5. 5 times 5 is 25, plus negative 75 would be negative 50, and then 5 times negative 50, so it's not negative 5. Negative 5, positive 5 doesn't work, because that'd be negative 500, so it must be negative 5. All right, yeah, I think negative 5. Yeah, negative 5 would work here. Would be a 0 of this, right? So again, negative 5 plus 0, and then you got positive 25 again for negative 50, and then positive 250 plus that is 0. So this will factor to x plus 5, right? Because again, negative 5 is a 0. And then these gave me the coefficients of the quotient here, the 1, negative 5, and 50 times x squared minus 5x minus 50. And then that factors even further. You got x plus 5, and then this quadratic would factor to x minus 10 times x plus 5. So you have another x plus 5. All right, so I got x plus 5 squared times x minus 10. So then my critical values are x equals negative 5, right? That makes the derivative 0. But also x equals positive 10, right? And you can do that too. 1,000, that might have been easier to see. 1,000 minus 750 minus 250, that's also 0. Make a number line. So again, first I'm doing on top here the number line for f prime. So again, at negative 5, f prime is 0. At positive 10, f prime is 0. And once again, knowing what we should know about polynomial functions, an odd degree with a lead coefficient that's positive should have negative values to the far left. Then negative 5 has a multiplicity of 2, so it's going to stay negative to the right of that. And it's not going to change sign at negative 5 with the even multiplicity. But then it will change sign at 10 with the odd multiplicity. And again, should have positive values to the far right if it's got an odd degree positively coefficient. So there is where the function will be decreasing, right? Function's decreasing over these intervals where the first derivative is negative. And then my function will be increasing, to the right of 10 where the first derivative is positive. All right, so now to talk about concavity, second derivative, right? F double prime would be 3x squared minus 75, and that's it. Now, if you want to factor this, you can pull 3 out, and then be x squared minus 25, and that's the difference of squares, right? 3 times x minus 5 times x plus 5. So my critical values for the second derivative, where the second derivative is 0, is at positive 5 and at negative 5. So I'll do that in the number line here, second derivative below. So again, negative 5 is one of those where the second derivative is 0. Now positive 5 is, again, between negative 5 and 10, I'll just put it here. That's where the second derivative is 0 as well. And once again, we got a quadratic, right? So parabola should be parabola opening up positive on both ends, right? So positive to the left of -5 for the second derivative, then 0 at -5, and then it should have, negative values between -5 and +5, and then positive values, to the right of 5. And that tells us that the original graph, the graph of this quartic function up here, degree 4, should be concave up to the left of -5, concave down between -5 and 5, and then concave up again, positive second derivatives to the right of 5. All right, so we're asked in this question, where is the function decreasing and concave up? So where does it have a negative first derivative and at the same time positive second derivative? So that's this interval here, all right? From negative infinity up to -5, you got decreasing concave up. Then it's decreasing concave down, so not that. And then it's decreasing concave up again, right, between 5 and 10. And then after that, it's increasing concave up. So the intervals, there's two of them, from negative infinity up to -5, decreasing concave down. And then from 5 to 10, decreasing concave down. So those are what I'll be entering. All right, so interval notation, right? So again, from negative infinity, so minus infinity, now infinity's in the basic keyboard, up to -5, right? So that for that first interval. And then the union symbol, right? They didn't say anything about commas, right? So back to the sets keyboard, union. And then just between 5 and 10, right? So the interval from 5 to 10, it's also decreasing and concave up. Wonderful. All right, so those two are done. So the only thing left now is that second derivative test with, the transcendental functions like that cosine example from way back earlier in the video. So this one has a natural log function in it. All right, so again, transcendental, not algebraic. So again, they give us a specific interval. We're only looking between, x equals 1 and 5. And we're looking for, for what values of x will this function be at the top of a hill, right? Will you have a local maximum value, or at the bottom of a valley where you have a local minimum value? Right, so let's take this function here. So this one involves a natural logarithm, right? You got f of x equals -2x plus 5 times the natural log of 2x. And again, we're only looking on the interval from 1 to 5, right? +1 to +5. So I take my first derivative, that would just be -2 plus, 5 times, and then remember the derivative of the natural log of something is 1 over that thing, but then times the derivative of the thing inside, then times 2. So the 2's will cancel. That's just 1 over x again. So you have -2, plus 5 over x, which if you want to get it together would be -2x plus 5 all over x, right? If you get a common denominator. So the critical values that are on the interval from 1 to 5, right? 0 would be one of them that's not in there, right? This is undefined at 0, but so is this, right? 0, you can't do the natural log of 0. So I'm not even worried about 0. So the other one is, what makes the numerator 0 here, and that would be +5 halves, right? This would be x equals 2.5, right? 5 halves, that's in this interval. And then I plug it into the second derivative, right? So the second derivative, I'm just going to look at it this way, would be 0, and then remember this is 5 times x to the -1. So that'd be -5 times x to the -2. So it'd be -5 over x squared. And when I plug this in, right, the value of f double prime at 5 halves will be negative, less than 0. Because, numerator's positive no matter what. You got x squared. And the the denominator's positive no matter what. And then the numerator's negative. Negative over positive will be negative. So f, we're on a piece of curve that's concave down at x equals 5 halves. So f has a local maximum, right, at x equals 5 halves. You'd be on part of a curve that's, curling down top of a hill. And that was the only one, right? So there is not going to be any valley. There's no local minimum. So local max occurs at x equals 5 halves, and no local minimum. So I go to that sets one. I put that empty set symbol in there if there's no value where there's a local min. Great. All right, it's the same thing. They give me a function here that's not algebraic, right? You got this exponential going on here too, along with some algebraic stuff, but this e to the 4x makes this transcendental. Over the interval between 33/8 or 4 and 1/8, 4.125, and then 65/8 or 8.125. So between 4.125 and 8.125, just between those values, we're looking for hills and valleys, local max, local min locations. All right. So here's the function I'm given. I'm going to put the minus up top. You got -5 times e to the 4x power in the numerator, and x minus 4 in the denominator. So derivative, again, we're only looking on the interval between 33/8 and 65/8, right? So again, between 4.125 and 8.125, right? If you want to write decimal form. So the derivative, right? I got to go through and do the quotient rule here. So it's, denominator x minus 4 times the derivative of the numerator would be -20 e to the 4x, right? Because it would be e to the 4x times 4 again with the chain rule, and then you got the 4 times -5 for -20. Then minus, and then the numerator, -5, e to the 4x times the derivative of the denominator would just be 1. All right, so no need for that, and then divided by the denominator squared. All right, so to simplify this a tad, this is, I'm going to pull out -5 e to the 4x, and if I remove that factor, you'd have, +4 still from this factor here times x minus 4, and then minus, -1. We'll put this together. This would be 4x minus 16 minus 1. So this is -5 e to the 4x times, and then 4x minus 17. That's in the numerator. All that divided by, x minus 4 squared, right? So this divided by x minus 4 squared. So the critical values that are on this interval, right, between 33/8 and 65/8. Right now, 4 isn't in there, obviously, right? And 4 isn't even part of the original domain, right? So don't worry about 4. That makes the denominator 0. So just really focus on what makes the numerator 0. Now, exponentials are not going to be 0, right? E to the 4x will be a positive number. So this is always negative, this -5 times e to the 4x. So what makes this 0 would be the 4x minus 17. All right. And 4x minus 17, that'll be 0 when x is positive 17/4. Now 17/4, that's 4 1/4, 4.25, which is bigger than 4.125. So this is in this interval, this 17/4. So now what we're going to do is, again, the second derivative test. So I need to take this here, find the second derivative, and plug in my critical value and see if it's positive or negative there. All right, so second derivative. So once again, I'm going to do quotient rule here. It's going to be ugly, but maybe it'll simplify nicely. So we got, denominator, x minus 4 squared times, and then the derivative of the numerator, I'm going to be doing the product rule again. So I leave the first factor alone, this -5 times e to the 4x, right? And the derivative, so leave the first alone, derivative of the second is 4, and then plus and then leave the second factor alone, 4x minus 17. And then the derivative of this first thing again would be negative 20 e to the 4x. All that in brackets there. All of this is the derivative of the numerator. So denominator, derivative of the numerator, then minus, the numerator, negative 5 e to the 4x times 4x minus 17 times the derivative of the denominator would just be 2 times x minus 4 to the first. And that's it. All right, and then all this divided by the denominator squared, so x minus 4 to the fourth. Okay. Now I'm just going to leave it this way because we're going to take our value, our critical value, and plug it in. Now, when I plug it in, this term is going to disappear here, right? That'll be 0 because of the 4x minus 17. Same thing over here. All of this would have a factor of 0 as well, so that's going to be 0. So the only thing that really is going to come into play here is this. Now, this negative 5 e to the 4x, that's going to be a negative number no matter what. It's going to be a negative because of the negative 5. E to the 4x is positive times that is negative. And then times 4 will still be negative. And then this x minus 4 squared will be positive. So I'm left with this negative times this positive, so I have a negative numerator, and again, something to the fourth power, a positive denominator, so I get a negative value overall, which means f has a local max again. All right, so a lot of these problems, it's been a local max, right? You've been at a point on the curve where it's concave down, has a negative second derivative. So it has a local max at this 17/4 value. And again, that was the only critical value in this interval, so no local min, no bottom of a valley. So local maximum occurs at 17/4, no local minimum. So again, I'm going to that sets keyboard and entering that empty set symbol. Great. All right, then one more, it looks like. I'm hoping one more. I'm about 3/4 done here. So another one where given a function over a specific interval, right, just between 0 and 3, where would any local maximum or local minimum values occur, if any? And this one's pretty similar to that other one that had a natural log in it. So function here, f of x equals negative 3x plus the natural log of x, but we're only looking on the interval, between 0 and 3. So first derivative be negative 3 plus, 1 over x, which if you want to put those together would be negative 3x plus 1, all over x. So my critical values that are in this interval from 0 to 3, again, obviously 0 is not working, okay, not even for the original function, so don't worry about 0. But what makes the numerator 0 would be a third. X equals 1/3. That would make this whole thing 0, and that's in this interval. So now I find the second derivative, right? The second derivative, again, it would be easy to look at it this way as, look at the first derivative as negative 3 plus and then x to the negative 1. So that'd be 0 and then minus 1 over x squared. So when I plug this in, the value of the second derivative at 1/3 is going to be a negative number again. All right, yes, because 1 over x squared will be positive. Then you have this minus 1 out front, right? So just like all the other ones, I hope maybe you'll come across one where the value of the second derivative is positive, and that means you're concave up, you're at the bottom of a valley, local min. But so far, right, in all these preview questions I've been getting, we've had a negative second derivative at the critical points for the first derivative. And at those points, you're at the top of a hill, right? You're at a point that is on part of a curve that's concave down. So you got to be at the top of a hill, a place where there's a local maximum. So f has a local maximum at 1/3, and that was the only critical value, right? So no local minimum. So local maximum occurs at x equals 1/3. Once again, going to that sets area for this empty set symbol, no local minimum in that particular interval. Great. All right, so that's it. All right, for the preview questions I'm getting on these three objectives from the second derivative test. So again, this was part 3 of the videos on this assignment. If you want to look at problems I've done from the first derivative test, go back and look at the part 1 for this assignment, the part 1 video I made. And if you want to look at the concavity and points of inflection questions that I received, go back and look at part 2. All right, so hopefully, watching me go through these here help you out when you're working on them on your own, and you can get through these, second derivative test questions yourself. And thank you very much for watching.